Welcome back to Beyond the Comfort Zone, talking shit with King-KAMBUF. We are diving deep today, and I mean really deep, into a curriculum that, let's be honest, few people outside the institutional scale design world ever get to see.
That's right.
This is not about, building a house. This is high stakes, globally networked, institutional scale architecture and engineering.
It absolutely is.
Yeah.
What we've got here is the Architectural Insights with King-KAMBUF Daily Interdisciplinary Mentorship Brief, and specifically the digest from Thursday, December 11th, 2025. This is for the practitioner, the architect, engineer, planner, who is, well, right at the center of these huge political, environmental, and tech forces.
It's kind of a shortcut, isn't it? A shortcut to understanding where the real liability, but also the real opportunity is going to be in the next, say, 5 years.
That's a perfect way to put it.
And this King-KAMBUF material, it just bypasses all the basic code discussions. It jumps straight into the strategic stuff. Verification, influence, systems alignment. We're talking about the kind of knowledge that decides if a multi-billion-dollar piece of infrastructure is even viable.
Or insurable, or functional 20 years from now. The biggest takeaway right from the start is that what an architect delivers is no longer just a set of drawings.
No.
It's evolving. It's becoming this highly sensitive instrument of governance and data production.
Okay, so our mission today is to really distill these next generation shifts. You've boiled it down to 3 main frontiers of transformation, right?
Yes, 3 big ones that are reshaping the whole field.
Yeah.
They demand a kind of convergence of expertise that, frankly, just didn't exist 10 years ago.
So what's frontier number 1?
The first one is that architecture has to fundamentally become an active, constant, information-producing system. And this is way beyond just, basic BIM. It's about creating real-time data flows, ensuring deep compliance, especially with global carbon accounting.
Okay, information systems. Got it. Frontier number 2.
Number 2 is a total shift in focus to adaptation and ethics. We're designing for climate instability, which means deep adaptation strategies are no longer optional. And, crucially, designing for thermal equity.
Thermal equity. The material actually treats heat mitigation as a civil rights issue, which is a huge reframing.
It is. It forces planners to see climate resilience not as some add-on, but as mandated civic justice.
And the third frontier.
That's all about operational precision.
Okay.
The kind demanded by the machine ecosystem. It's the necessity of engineering down to, sub-millimeter tolerances so that our built world can integrate with autonomous logistics, with robotics, with these incredibly complex sensor systems.
Right, where serviceability becomes more important than just pure strength.
Exactly. And as we get into these, we'll unpack some amazing concepts, things like thermal equity mapping, the danger of audit latency, and even the chilling idea of modeling stack effect weaponization risk.
Okay. Stack effect weaponization risk. We're definitely coming back to that. Let's start where the money and the mandates are. Let's talk about the building's data trail.
So we kick off with what the source calls the industry pulse around interoperable carbon accounting. This is a massive systemic shift, and it's being driven almost entirely by the financial sector.
Not by architects themselves?
No, by multinational clients and their financiers. They're now required to submit cross-platform carbon reporting that covers their entire supply chain, from raw materials to final product. And that forces the design teams to get on board.
Okay, but stop there for a second. How does that really change the game for the architect? I mean, what does it mean for their actual liability profile?
It changes everything. Design teams can't work in a bubble anymore. They're being forced to adopt these unified data standards that have to be, immediately compatible with the systems used by a concrete manufacturer in one country, a shipping company in another, and the environmental agency in the client's home jurisdiction.
So the data has to be seamless across all those platforms.
Yeah. You hit the key word liability. The sources are very clear. Architectural deliverables are now shifting into auditable supply chain documents.
Wow. Okay, so my drawing set isn't just for the builder anymore.
Exactly. It's the fundamental accountability ledger for the embodied carbon of that entire structure. So if the data in your model conflicts with the data from the steel supplier 5 years later during an audit.
Yeah. The client gets hit with penalties.
Right. And that liability often traces right back to the original source of the design data, which is the architectural engineer.
That's a very stressful reframing. It means every single choice, the structural system, the specific concrete mix, where the steel came from, it's not just a technical decision anymore.
It's a data input, an input into a carbon management system that will be scrutinized for years, long after the building opens.
So the challenge presented in the briefing is what? To build a strategy around this.
A profound one. It says, develop a design strategy where your material choices, your structural systems, your construction phasing, all of it feeds directly into a real-time, cloud-based carbon reporting system. It demands a level of foresight that, honestly, architectural education just hasn't traditionally taught.
And the sources point to specific groups driving this, right? The Environmental Ledger Standards Initiative and the Built Environment Carbon Interoperability Alliance. For anyone listening who's not familiar, what are these?
They're key. They're alliances, usually driven by the big players, financial institutions, insurers, huge developers, the entities with the most financial risk from climate regulations.
So they're setting the rules.
They're standardizing the digital protocols, the
Yeah.
APIs. The goal is simple. Create a global language for carbon data. So the embodied carbon data from a steel mill in Asia can flow seamlessly into your BIM model in Europe and then into the developer's ESG reporting platform in North America.
Okay, so the architect is now responsible not just for the building's physical performance, but for the fidelity and the speed of its data trail.
Precisely. And that brings us directly to a really critical concept from the RE study block, analyzing audit latency.
Target latency. I love that term. It's so
Right.
specific. It captures that time lag, right? The gap between an action, like a truckload of low-carbon timber arriving on site, and that fact being officially registered and verified in the client's global ledger.
Exactly. And the source is blunt about why that latency is so dangerous. Slow reporting leads to catastrophic regulatory penalties.
And supply chain bottlenecks.
Absolutely.
Right.
Imagine your client is counting on a tax credit tied to a carbon threshold. If your data system takes 3 days to certify the embodied carbon of a major concrete pour, the client might miss their filing deadline.
And that could mean losing financing or even having the whole supply chain frozen. We're talking millions of dollars in repercussions just from a data delay.
Which proves the point.
Yeah.
Architecture is now fundamentally an information-producing system. The speed of the data is as valuable as the strength of the steel.
Wow. Okay, so the briefing challenges the architect to demonstrate this with a 10-item carbon accountability checklist. We should probably walk through a few of those. What are we talking about here?
Yeah, Les, this checklist basically defines the new minimum standard. For instance, number 1 is material origin verification. You have to track the exact manufacturing plant and its energy source to verify the supplier's emissions claims.
So no more taking their word for it.
None. Number 3 is real-time comparison against baseline budgets. Your design system has to constantly track embodied carbon against the contractual limit and flag any variance instantly.
What about change orders? They always happen.
That's number 9. Change order carbon impact analysis. Every single change order has to automatically trigger a carbon impact statement showing the plus or minus to the ledger before it's even approved.
That is intense. You're not just designing a high-performance curtain wall anymore. You're signing off on the entire data infrastructure that proves its high performance.
It's a massive paradigm shift. And that long-term accountability, that brings us to structural health and this idea of continuous diagnosis. What happens when the sensors themselves start to fail?
Right, here's where we get into some really interesting new failure modes. The briefing highlights that embedded corrosion monitoring systems are going mainstream, especially for big infrastructure like bridges and tunnels.
The insight here is that a structure is never really finished. It's under continuous diagnosis. So the design has to account for the entire life cycle of data production, which includes replacing the sensors themselves.
But the sources pivot immediately to the risk of that, to this concept of sensor redundancy drift. So what happens when the monitor fails before the thing it's monitoring?
That's the new failure mode. Sensor redundancy drift. The sensors are often cheaper and more fragile than the concrete they're embedded in. They degrade, they lose calibration. And if you get a false negative, a corroded sensor telling you everything is perfectly fine, that can lead to a catastrophic failure down the line because you skipped necessary maintenance.
So you're dealing with data failure, not just material failure. How do engineers even manage that?
The workflow is complex. First, you use statistical cluster analysis. You compare the weird reading to the sensors around it. If one sensor drops, but the 7 next to it are stable, it's probably just that one sensor that's bad.
Okay, that makes sense.
Then you do targeted non-destructive testing. You send a team with ground-penetrating radar to that exact spot to get physical data to verify what the sensor is claiming. It's all about distinguishing signal from noise in a real-time data flow.
It's information mastery. That's the new skill. Okay, with that data foundation set, let's move to the next frontier. Designing for a planet that is, well, fundamentally unstable. So the second major theme, deep adaptation, it starts with a really profound ethical pivot on how we think about urban heat. We're talking urban thermal equity.
We are. The sources confirm cities are adopting thermal equity maps. And these aren't just heat maps. They identify heat-burdened populations based on income, health vulnerabilities, and lack of access to shade and cooling.
So heat mitigation is now being defined as a civil rights issue.
Explicitly, championed by groups like the Urban Heat Justice Collaborative. It means a hot, treeless neighborhood is no longer seen as just a bad design outcome. It's an injustice that requires mandated thermal relief.
So things like shade corridors, cool roofs, they become a civic necessity, like clean water.
Exactly. And this poses a huge innovation challenge because the brief asks for a district cooling strategy that improves thermal equity without relying on energy-intensive mechanical systems.
Right, because just adding more AC units just makes the overall problem worse. The heat island effect, grid load.
Precisely. So we're being forced back into passive design mastery, but with this very specific social justice goal. We're talking about a thermal equity district spine, a major urban corridor designed purely to cool people down using low-energy solutions.
But the briefing adds a layer of nuance here, a long-term reliability risk. It talks about surface albedo drift over time. So what? The reflective surfaces get dirty?
They get dirty, they erode from acid rain, they get damaged. Their albedo, their reflectiveness drops. A design is only ethical if its performance is sustainable. If your cool corridor stops being cool in 5 years, you failed the mandate and left that vulnerable population exposed again.
So maintenance is now a core architectural concern.
It has to be. The maintenance budget is a social justice requirement. And this moves us from heat adaptation to water and into this unsettling but very real domain of planned impermanence.
Right. Signal A in the brief says governments are actually drafting policies to pre-approve temporary urban districts, districts that are expected to relocate inland within 20 to 40 years because of sea level rise.
This is climate retreat becoming codified policy.
That is a seismic shift in planning. It means design is moving toward planned impermanence, where portability and modularity are their civic virtues. How do you even begin to design a city that's meant to move?
The focus is on the structural and material constraints. Portability means standardized components, universal connections, materials designed for disassembly and reassembly without waste. The structure has to be fundamentally separable.
And the briefing says architecture has to express dignity even when it's temporary. These can't feel like refugee camps.
No, dignity is expressed through permanence of identity, even if the material is temporary. Using civic markers that are designed to be moved, recreating central gathering spaces quickly in the new location to give people a sense of familiar ground.
The geotechnical reality of this is wild. The study module talks about analyzing foundation migration zones. What does that even mean?
It means the ground under your feet is temporary too. These are zones where mobile soil bands, thanks to rising water tables, are going to cause differential settlement. One corner of your foundation will sink faster than the other. The ground is a moving fluid.
So you're not designing for a static load anymore. You're designing for the foundation to survive a shifting, liquefying ground plane.
Exactly. Which brings us to the relocatable district core. This is the brainstem of the temporary city. It houses the critical infrastructure, the data center, the emergency ops center, and it absolutely must survive the move intact.
This is more than just modular construction. This is about design disassembly. And that logic applies to life safety, too, with modular egress logic.
Yes. Because these districts will expand and shrink, the exit paths have to reconfigure safely and instantly. The deep lesson here is that egress isn't a static drawing. It's a dynamic system capable of reassembly. Life safety has to follow the people, not the building.
So your fire separations, your command centers, they all have to be plug and play.
They do. Temporary does not mean permissive. Your life safety systems have to be permanent grade, but fully mobile.
Remarkable. Okay, the level of precision this all requires is astronomical, and that brings us to the next ecosystem we have to design for, the machine.
This third transformation is all about the extreme convergence of structure and automation. The industry pulse is clear. Structural engineering now has to model machine behavior loads. The focus is shifting from human use patterns to, well, to robots.
This is a radical change. We're talking about freight hubs and distribution centers being designed for autonomous vehicles, for drones. What are the specific demands they place on a building that people just don't?
The core demands are precision and rigidity. Ultra-precise tolerances in ground flatness, vertical clearance, dynamic load tracking. The structure has to be a predictable, stable environment for an algorithm to navigate.
Which brings us to the precision mandate. The study block asks why autonomous logistics hubs need precision flatness zones. What's the big deal about a few millimeters of deviation?
The consequence is operational failure. These AGVs, these automated vehicles, they rely on precise spatial data from markers in the floor or LiDAR. If the floor has a small dip or a vibration, the robot sensors can drift, has to constantly recalibrate,
Which slows it down, drains the battery.
and can destabilize the load. A tiny dip that a human forklift driver wouldn't even notice can completely throw off an algorithm. It's a fundamental shift. Serviceability criteria are now outweighing pure strength.
It's not about if the floor will collapse, it's about if the robots can run on it at full speed.
Exactly. If the floor can hold 100 tons but isn't flat enough for your $1 million robot fleet, it's functionally useless.
This must create an immediate design conflict. The challenge in the brief is to create a structural base system that works for both human forklifts and autonomous robots. They have conflicting needs.
It's a brutal negotiation. Human forklifts need wide turning radiuses, clear sightlines. Autonomous systems thrive on dense, rigid grids with zero deviation. You can't optimize for both without a very expensive compromise.
And this plays out in the scenario from the briefing, the autonomous logistics crash event. Let's walk through that.
Okay, so it's a nightmare scenario. A new distribution hub, it's 92% complete, massive pressure to launch. An autonomous forklift misreads a depth marker and collides with a mezzanine column, deforming it. The entire site is now paralyzed.
So the conflict is, who's at fault? Was it a design tolerance issue, bad installation, or was the robot just not calibrated correctly for the as-built conditions?
And you need a shared truth model to figure that out. The developer, the robotics vendor, the insurer, the structural engineer, everyone has to agree on the root cause.
So what's the workflow? What are the critical steps?
First, immediate structural deformation mapping. The engineer scans the column to quantify the damage, figure out what failed and how badly.
Okay.
Second, robotics diagnostics. The vendor pulls the machine's data logs, velocity, path deviation, and crucially, the sensor logs. What did the robot think it saw right before the crash?
And the political part.
The most important part, agreement on a single authoritative root cause model. Everyone has to sign off on one store design, installation, or calibration, because until that's settled, liability isn't assigned, and the insurance won't pay for the repair.
And the final step is retrofitting. But retrofitting for machine vision, what does that even mean?
It means making the building talk back to the robot more clearly. You might have to paint high-contrast reflective lines on the floor, install passive RFID tags, or add physical barriers made of materials that give the robot specific sensor a really strong, clear signal. You're making the architecture a primary communication medium for the autonomous system.
The building is feeding data back to its user, which in this case is a machine.
Fascinating. Okay, let's move to the final and maybe most complex frontier, architecture for governance and crisis response.
Our final section is about architecture designed to manage human populations under extreme stress. This is where massive infrastructure meets governance intelligence. And the flagship project here is the Intercontinental Climate Mobility Coordination Center, the ICMCC, a hub for coordinating massive cross-border climate migration.
And the suggested angle for designing it is to think of the building as a global choreography engine. It's a political and infrastructural instrument designed to shape human movement ethically and predictably during a crisis.
So the building's function is literally to manage flow, data, and diplomacy under extreme conditions. The challenge is designing a spatial sequence that reduces diplomatic conflict while increasing decision precision. How can a hallway reduce tension between two countries?
By understanding that circulation is a diplomatic interface, the arrangement of briefing rooms, the path an envoy takes to the secure data center, the physical proximity of different national desks, these choices can mitigate tension. They can reduce what the source calls protocol collisions.
This brings us to a whole new category of load management: political occupancy.
Exactly. We have to analyze organizational surge loads. And the source makes a crucial distinction here. This isn't about the number of people in the building. It's about coordination intensity loads.
Coordination intensity. So that's the pressure on the systems, the network, the communications when a crisis hits. You might only have 50 people in a room, but if there are 50 high-level decision makers from 50 different countries during an emergency, the sheer volume and sensitivity of the data being exchanged creates this huge non-physical load.
It's like maximum network bandwidth being consumed by the smallest number of users, and that expands into jurisdictional interoperability loads. When multiple agencies, a foreign military, a border agency, the UN are all in the same space, their different protocols and legal mandates can clash.
Protocol collisions. So one agency uses NATO standards, another uses UN standards, their command structures conflict. And that friction creates a tangible load on the building's operational capacity.
Yes. The deep lesson is that occupancy in a governance hub is fundamentally political, not just numerical. A hallway isn't just a hallway. It's a diplomatic interface designed to smooth that political flow.
And there are subtle operational loads that affect this too. Let's talk about acoustic decision interference. We don't usually think of acoustics as a life safety issue.
But it becomes one here. Poor acoustics, too much echo, noise bleed between critical zones, can distort speech and dramatically slow down emergency coordination.
So if you can't clearly hear a critical coordinate or a change in status because of background noise, that delay could be measured in lives lost.
Absolutely. So sound has to be analyzed as an operational load. Sound absorption isn't a luxury. It's a life safety mechanism that dictates the speed of command execution.
This holistic view of risk extends outside the building too, which brings us to this big ethical shift. Land use harm audits.
Signal C is a big one. New planning models are starting to require agencies to quantify the negative externalities a project produces before it's approved. Displacement, noise, microclimate shifts.
So design excellence now requires acknowledging what your project disrupts, not just what it creates. You have to prove with data that you're not actively causing measurable harm.
Which means you have to analyze harm propagation vectors.
Ah.
How do noise, heat, and shadows spread from your site? It's a physics problem disguised as policy.
Okay, let's look internally again at the most advanced risk modeling in this brief. This one sounds, frankly, it sounds terrifying. Stack effect weaponization risk.
It is a chilling concept. The stack effect is basic architectural physics. Hot air rises in a shaft. We use it for passive ventilation all the time. But the source asks why high-density towers now have to model this as a weaponization risk.
The concern being that the passive stack effect could rapidly spread smoke, or worse, a chemical or biological agent.
Exactly. It turns a benign physics principle into a massive life safety threat. A contaminant introduced on a low floor gets distributed by this powerful natural chimney throughout all 80 stories of the building in minutes. The passive design becomes an amplifier of disaster.
So what are the mitigation strategies? How do you fight physics?
With active systems designed to collapse that stack effect. Sophisticated mechanical pressurization zones, redundant vertical compartmentation, smart elevator shafts that can seal themselves off and neutralize the thermal difference to stop the chimney effect from working. It's actively countering natural physics with engineered intervention.
That brings us to the end of this incredibly dense material. What's the final synthesis for you? Looking at these frontiers of information, adaptation, and machines. Hashtag tag outro.
I think what's truly revolutionary here is the convergence it demands. The days of siloed expertise are they're over. Architectural mastery now requires a fusion of governance, intelligence, understanding political loads, climate ethics, with extreme engineering precision for robots and audible data.
Yeah.
The building isn't an object anymore.
Right. It's a networked ethical instrument. It's a political interface.
All at once.
So for you, the learner, you can't succeed by specializing just in aesthetics or just in structure anymore. You have to understand how your choice of facade creates an information system, how your foundation responds to climate policy, and how your floor plate interacts with an algorithm.
And these insights, they offer you a massive shortcut. They show you what you'll be expected to master not in 10 years, but today. The ability to think across systems, across disciplines. That's the new measure of competence.
So as you reflect on this deep dive into the KING-KAMBUF briefing, we want to leave you with the two big philosophical questions that really underpin this entire conversation.
The first question, given the rise of automation, how must architecture evolve when buildings are used by machines as much as by people?
And the second, thinking about our unstable world. How can architecture express stability when its context is unstable? The answer to that one might just define the next century of our built environment.
Those are the challenges.
And that is where we'll leave it for today. Thank you for joining us on Beyond the Comfort Zone Talking Shit with KING-KAMBUF. We'll catch you on the next high-level brief.